Bless you. So it's going to be the quantitative analysis of copper ore. So you're going to get an unknown copper sample from the stockroom, and then you're going to process that sample in a couple different methods to try and determine the composition of the copper ore. Right? This experiment is going to be done individually all the way through it, just because it's more fun to do it that way. Okay? The lab report is a whole report. So for those of you that have been doing all of the individual sections, this is a good lab report to do all of the individual sections for. I will grade each section. Okay? Starting off with, as we've done before, what should we expect to see in the title? We could go through with quantitative. I would probably get away from that term just because the other terms that you would use imply quantitative. So I wouldn't use quantitative.
Sorry, before I forget, when is the ester lab due?
Again, what other words? There we go. There's a big one. Spectrophotometric. That's probably a good thing to include in the title. All right, we'll look at what that means in a little bit. What else? Could go through with the analysis. It's kind of a description of spectrophotometric, so it's not a bad word to include. It would probably help you cohesively bring the title together. Copper ore is probably a really good one to include. After all, that is what you are evaluating in this experiment. And the last really, really big one, the electrogravimetric phrase, which brings in electrolytic. Okay? So we've got those all kind of summarized up there. The next part of this would be your abstract. What would we expect to see in the abstract? Probably all of those words again, okay? With the intent of saying that your goal of this experiment is to determine the percent copper in your sample. Okay? And you do that with two methods, the spectrophotometric method and the electrogravimetric method. Okay? What would you do then next? We said the goal is to get the copper ore. Okay, we don't need a methods because we already said the methods. It was determine the copper ore by doing spectrophotometric and electrogravimetric. There's your method section. So we could now jump to the results. What would your results be? Whatever the percent copper that you got from both methods. Okay. Then what we follow it up with? There isn't really anything to explain. It's copper. I mean, you have a percent copper. So beyond that. What's that? That's your result.
Is that a discussion?
That should show up in your discussion as well. How about a success? Was your experiment successful or not? Okay. Again, that is your decision to decide that. Okay. If it's not there, you definitely lose points.
Are we going to be looking at what it should be?
I haven't quite decided on telling you what it should be or not. I don't think I know quite yet. We could then move into the introduction. So our why behind this is sample analysis. Okay, we would like to come up with some methods to identify an individual sample. In this case, we could spin our own little argument or little story behind the lab itself. We're trying to determine the copper in a particular ore sample. Why might that be an important thing to do? Well, if you're trying to decide if it's worth trying to pull copper out of the ground, it might be worthwhile knowing how much copper is present. Because if there isn't enough copper in the ground, it doesn't make sense to try and pull it out. Because the amount of effort you put in is going to be way more than you could get out as far as the money goes. Okay? So mining companies would run similar processes to this, trying to determine how much metal is actually present so that when they put in the investment to pull the metal out, they actually have or make money on it. They turn a profit. Okay? So that's kind of the why behind what we're doing. We could go through into the theory on the why and trying to learn all that, but we can push that into the how and our complications. Okay? As far as the how goes, we're going to be doing two methods, the spectrophotometric method and the electrogravimetric method. Spectrophotometric, if we break that word down a little bit, spectro means, I really like this breakdown, I'm going to do it anyway. How about photo? Come on. I can't draw. What the heck? A picture, so we're looking at a spectrum picture. So what we're going to do is see how our individual sample responds to light. Okay? How we're seeing individual pictures. Okay? So we're going to be taking ultimately a picture of our sample across a broad spectrum of light. And the hope is that we could then correlate that back to something useful, i.e. the concentration or the amount of copper within the sample. The metric is ultimately just measuring. So what we're looking at is a light picture measurement. Okay? So kind of neat. What we're going to be doing there is using ultraviolet invisible light. In fact, actually, we can cross out the ultraviolet. I don't think we hit ultraviolet. We're going to use just visible light to determine our spectrum. Okay, so what we're going to do is use that to see how our sample responds and hopefully be able to tie that back to concentration. Okay. The other method is we're going to use Electro Gravimetric. What is Electro? Electricity. So somehow or another we're going to introduce electrons into our reaction or into our solution to get some kind of change. What's the gravi mean? Where have you seen that kind of term before? Gravity. We're looking at a weight. Okay? So we're going to use electricity and weight to do a measurement. Okay? So ultimately that goes back to the two things that we've broken it down to already, weighing it and a term that we haven't introduced yet, either in lab or in lecture, electrolysis. Okay? And we'll run an electrolysis calculation today, and we'll look at a little bit more details on that in lecture and probably later in this lab. Okay? So complications. When we look at the spectrophotometric version of this, what happens? So if we take a look at light and we shine it at a copper sample. Okay, so if I put a copper solution up here, what would you expect to see? How would you describe that copper solution? Anybody know? It's colored, it's blue. Okay? What happens if I add more copper into that solution? It becomes more blue. So what does that mean? There is a correlation between concentration and the intensity of the color. Okay? That observation or that relationship was first described, or first given credit to at least, so I believe his name is Beers, last name Beers. So you get the Beers law relationship, and what that's correlating is light absorption to a concentration. Okay, and we'll break that down a little bit too. So the first thing that we might need to do with that is come up with some way to standardize so that we know what light absorption means. How does that correlate back to a concentration? So we're going to have to come up with some standard solution so that we can then compare our unknown back to that standard. Okay? When we get into the electrogravimetric process, okay, this is going to be a relatively error-free experiment because there's not a whole lot to do. Really, all of the error is going to come from the balance. So you're just going to end up weighing your sample before and then weighing it again once you find out how much copper is in it. You just do a simple percent composition. The question becomes is how do we get that copper out of the ore? And that's what the electrolysis is for. So that's the electricity. One of the complications of this one is potential side reactions. So if we aren't careful, we could potentially push other side reactions to occur, which could limit our yield. Okay? But for the most part, there really isn't any error associated with this. You would actually have to screw it up to actually get it to go wrong. Okay? So it's a pretty straightforward one. One of the very first complications that we're going to have is everything needs to be in solution. Right? To do the electrogravimetric stuff, we have to have electricity running through our sample. To get the electricity into our sample, we can't just put it directly into a dry powder because the electric current's only going to hit where our electrodes are. So we're going to have to get our copper dissolved first. Okay? So our very first step with all of the individual procedures is to turn your copper your copper ore into a copper ion. Once in that state, we can then do the electrolysis on it. We can then also do the spectrophotometric analysis. Okay? So to get it into solution, I definitely didn't do a good sequencing on this. So if we were going to start with the electrolysis portion of it, to get our copper ore into solution, we'll first get the ore from the stockroom, and then we're going to dissolve it. Okay, we're going to add concentrated sulfuric and nitric acids. These are both extremely corrosive and extremely dangerous. Please, please, please be careful with these when working with them. Okay? These compounds will dissolve pretty much any organic material in there. We want to get rid of the organic materials because the organic materials can react with the electrons in our electrolysis experiment. They can also change the absorbance. Okay? So we want to try and remove that organic material. These acids will dissolve it all so we don't have to worry about it. Okay? Pretty much remove all that color. The other thing that they're helpful for is that they will react with copper metal and turn it into copper ion. Okay? So that's going to take our entire ore sample and hopefully convert it directly across into a complete and even solution. So we don't have to worry about particles floating it or anything like that. Okay? To speed this process along, because it is a redox reaction, we want to help facilitate that, and to do that, what we'll do is heat the reaction up, okay? Which adds another level of hazards to this. Not only are you working with concentrated nitric and sulfuric acids, but now you're working with really hot concentrated nitric and sulfuric acids. Okay? The other issue that you'll find with this is that when you heat these two acids, they do react with each other to generate a noxious fume, some nitrogen oxide compound, which is very, very toxic, and we don't want to breathe that in. So how can we limit our exposure? We'll do all of the heating process in the fume hoods. Okay? Do not dissolve your copper ore with the nitric and sulfuric acid at any point outside of the hood. Okay? It needs to stay in the fume hoods. We really only have 3 available to work within, and within each of those hoods you can only get 4 hot plates in there. So it'll be a bit dicey to kind of deal with people, but we should be able to do it okay. Questions about that? At that point, we now have it into solution. So, and this would be for just the electrolysis portion at this point. Okay? So now what we could go through and do is kind of divide up. The organization on this is awful. I would recommend that everybody attempt to do the electrolysis first. The electrolysis is going to be our clutch point. Okay? To do this, we have to use an electrode that won't decompose or do any side reactions. What metal would be a good reaction to use, or a good material to use? Okay. Platinum, because the answer's up there, but other options, gold. Okay. Why are those materials considered so valuable? Because they're really stable. They won't react or decompose under high electric currents or with other materials. So to get them to dissolve or do anything else is really, really difficult. Okay? Problem with that is that these metals end up being very, very highly valued. So a single platinum electrode that you guys are going to be using is worth upwards of $2 or $3 grand. Okay? Which means we don't have a lot of them, which means to get them, you have to give the stockroom some collateral. Okay? Usually they're okay with just an ID. Sometimes it's an ID and a key to your car. Okay? So that there's no way you can leave without it. Okay? So just be aware of that. Because there's only 6 electrodes, Only 6 people can do this experiment at any given time. Everybody needs to make the solution. So if you immediately get started on making the solution, you can just store that solution for a later date when you go through and do the electrolysis. Okay? So I would recommend that once we're finished talking here, that everybody gets their unknown and immediately starts the dissolving process in the concentrated nitric and sulfuric acids, okay, to get that solution ready to go. The first 6 people that have their solutions ready can then immediately get the electrode, and then I'll talk to you more about how to use the equipment in the other room. Okay, you guys remember the blender looking things at the end of the room in our equipment room? Anybody? Yes, that's what you're working with. Okay, so you'll be playing with those today, at least 6 of you. That whole process takes roughly 30 to 40 minutes, maybe upwards of an hour. So if someone wants to, after the first wave goes through, we might be able to sneak another set of students in. Okay, but it's kind of up to you if you want to try that or not. You'll probably push your limits on time. Okay. So where I wanted to go was, what do we end up doing with this? Okay. So we kind of got, at least in a lecture, to a point where we could sort of talk about this. What we're going to end up doing is pumping electricity into our cells, or into our solution. Well, what's in solution is our copper ion. What we want to do is get the copper ion not to be a copper ion. So we want to turn it into copper metal. How can we get it to turn into copper metal? What does it need to balance this equation? Is this equation balanced? No. What's wrong with it? Charges aren't balanced. How do we balance the charges?
Add electrons to those.
We need to add 2 electrons to our reactant side. Okay. The equipment we're going to use is kind of nice. It will act as an electron source. So we can dip some electrodes into our solution of copper ion and then pump electrons into it. Okay. That electric flow, or the amount of electrons pumped in, is going to get recorded in a unit known as amperes. Okay? I believe for this experiment you're going to run at roughly 2 amps. Okay? Any electrical engineers? How do you get amps? Actually, I think I remembered it. It's 1 coulomb, so the charge of an electron per time. Okay. Whoops, I should set this up so we can cancel some units. We get 1 coulomb per second is 1 amp. Okay. So our amps will cancel and we will have coulombs per second. Okay. We want to pump in enough electric current to completely convert all of the copper ion across. So we're going to run it for X number of time. Okay? So what we could do is to get rid of the seconds by multiplying by a time. Okay? We can convert that time into seconds. I'll leave you guys to figure that out. Pretty sure you all can get that one done. At this point, we now have coulombs. So we have a charge that we've pumped into the reaction. We need to come up with some way to relate this charge back to some mole amount so we can use our balanced equation, because this is the charge for our electrons. To do this, okay, or an old famous guy happened to come up with a way to relate the amount of charge in a mole of electrons. Okay? This is known as Faraday's constant, 96,485. Whoops. Nope. Yep. Nope. I did that wrong. Sorry. We want to get rid of coulombs and turn it into moles of electrons. This is why we set up our units. Turns out that that value, or that relationship, is 96,485 coulombs in 1 mole. That was first discovered. We're given credit to Faraday. It's known as Faraday's constant. Okay? This is really helpful because now we know the moles of electrons we've pumped into the reaction. Where did those moles of electrons go? They went in to react with copper. So what we could then go through and do is convert the moles of electrons into moles of copper that we should be able to get out. What's the relationship between these two? I think you mean 1 to 2, right? 1 mole of copper is 2 moles of electrons. How do we know that? That comes from our balanced equation. Okay, time is an experimental value. This is a unit conversion. And this is experimental. What does that then tell us? For that amount of current, we should be able to now convert to moles of copper. What we can do is take this a step further and convert this into grams of copper. How do we convert from grams from moles? We can use the molecular weight. Was it 64 or something? 63?
63.5463 is what that says.
And we now have a theoretical amount of copper that could be produced given that amount of amps and that time. Okay? What we've done is an electrolysis calculation. You will see this in lecture, it just won't show up on exam 3. Okay? All this is unit conversions. You just have to know what things you're converting at each stage. How does this relate back to the experiment? Well, what's going to happen is you're going to stick your electrodes into the solution and we're going to pump electricity through it. Copper is going to then start to go from copper ion into copper metal. Where's that copper metal going to form?
On the electrodes.
On the electrodes. So what will end up happening is that one of your electrodes, this is going to look awful, but it's roughly what you should see. One of your electrodes is going to start to get copper metal forming on it. Why is that helpful? So this is the electro part of this. The other part of this experiment was gravimetric, which was weight. What happened to the mass of the electrode? Got heavier because there's copper metal on it. Okay? So what we can go through and do is weigh the electrode before and weigh the electrode after. The difference between those is the copper that was in the solution. Okay? If we want to know the percent copper in our ore, what would we need to know?
Mass of the sample.
The mass of the ore sample, and then our copper from our electrode. Okay? You will not be using the entire ore sample, so you have to make sure that you get an accurate weight before you do all the dissolving process, because you're going to do it once for the electrogravimetric, and then you're going to do it again for the spectrophotometric. Okay? Questions about that?
Is it 3 to 4 grams each time?
Whatever it says. Does it tell you to calculate it, or does it just tell you the number?
No, it just says 3 to 4
Okay,
grams.
good. Okay? So when you get into lab, like I said, immediately try and get this set up, get it dissolving. This is the clutch experiment. You want to be the first to be done with this experiment, okay? Which means get it ready to go as fast as you can, and then you can make sure that you're ready to run everything else, okay? And you should get done early, if not on time, with the whole experiment, okay? Questions about your electrolysis? Why did we do that whole amperage calculation? That doesn't tell us the weight of the copper. Our copper here is in black. Why do the stuff in blue? But why do we need to convert? We get our answer without doing anything in blue. What we're going to do is look at the efficiency of our electrolysis process. Okay? So the answer in blue would be the theoretical maximum amount of copper that we could have gotten out. We can then compare that back to the copper that we actually got out, and we now have an efficiency of our electrolysis. Okay? So our efficiency will be our copper electrode divided by, what do we want to call that? Our, shoot, I don't know what to call that. Let's call it theoretical. Okay, and that's how you would calculate the electrolysis efficiency, is by going through and running that. Okay, yes?
So I'm having trouble reading. The second bit, does it say 1/1 times CS?
1 coulomb per second.
Okay.
So this is 1 coulomb per second.
And then the one that underneath the 96,000, what does that word say?
Faraday.
Faraday.
Okay, questions about that? Okay, this experiment is relatively boring. If 6 of you are in there, you can get one person to kind of watch all of the experiments while the rest of you then go off and work on other things, and then kind of alternate so that one person doesn't get shafted. Or you can just shaft them, that's fine too. Okay. This is only part of the experiment. So everybody that's getting ready to leave to the lab, what happens while you're waiting for this to occur? Okay. You could just sit around and wait, but then you definitely will not get done on time. Okay, and you will lose stuff. So what you can do is move to the next part of the experiment, our spectrophotometric part. Okay? According to Beer's observations, what he found, or was able to determine, was that the absorbance of an individual sample was equal to some constant times the path length times the concentration of our sample. Okay? So what this is generating a 1-for-1 relationship between absorbance and concentration. Okay? Concentration, in theory, we should be able to determine. The path length, we could just look at whatever sample we're using. So if we have a sample that is longer, the light has to pass through more of that sample. We end up increasing the likelihood that it's going to hit and be absorbed by our individual molecules. So the path length does play a role in this. Okay? The next thing is this constant. Okay? To be able to determine all this, we need to know what that constant is. If we don't know the constant, this calculation is pretty useless. Okay? So what could we go through and do to determine that constant? Or said another way, does this equation carry a particularly interesting format? What is B? Try again. Zero. There is no B in this case. It intersects at 0. Does it make sense? If we have 0 things present, To absorb light, what should happen to the light? Should it absorb any light? No, we should have a zero absorbance. So it makes sense that our y-intercept be 0, okay? Because zero concentration means zero absorbance. What about x? We can make that be our concentration. I would actually take it a step further and also make it the path length. Why would I include the path length in x? Is the path length something that we can easily determine? The path length is the distance the light passes through our individual sample. If I tell you your sample is this long, what's the path length? You stick a ruler between my fingers and you measure, right? Can you measure that? How about it's this long? Can you measure that path length? Yes. Path length is a very easily determined observable. Okay? So we can include the path length into our x term. Okay? Or we could group it with the constant. It's not going to matter. It just kind of depends on what you guys want to go through and do. Okay? What is m? That would be our epsilon, which I just said was a constant. The more appropriate name for it is the extinction coefficient. Every compound has its own extinction coefficient. So for an individual experiment, we must determine, or for an individual compound, we have to determine what that extinction coefficient is. So what we will go through and do is determine or set up a sequence of standards. Within those standards, we will know the concentration because we made them. Okay? We can then determine the absorbance of those samples. How? You all read the procedure. What do? Take the sample, hold it up to the light, and say that's roughly half of it is absorbed. Yes? No? How about 40% of it's absorbed? 30%? 10%. Our human eye does not quantify. What do? We make a digital eye. That digital eye is our absorption machine or our spectrophotometer. What that will do is look at the absorption of light. Okay? So we can then record for each of our individual concentrations the amount of light that passes through that sample, relate that to an absorbance, and then we can then go through and do what? Graph our concentration versus absorbance. In theory, what would we expect to see? As we increase the concentration, the absorbance increases. The slope of that line is then related to our extinction coefficient. How is that helpful? Well, we can now take our unknown sample where we don't know its concentration, but what can we do with it? We can test its absorbance. And let's say our unknown has that absorbance. What does that mean its concentration is? We now know our concentration of that sample. Once we know the concentration of the sample, we can back calculate how much copper was in that individual sample. Okay? It requires a bunch of unit conversions, molarities, all that sorts of fun stuff. When we actually have numbers to work with, we can run through some sample calculations with that. So, to do this experiment, we've got a couple issues. Number one, we need standard solutions. Okay, so one of the things that you're going to have to go through and do is make a whole bunch of standard solutions. That would be parts A and C, okay, of part 2. Okay, so there's a whole bunch of different steps being referred to in this. You can go through in the exact sequence that the lab procedure tells you to do. I don't recommend it because I think this goes a lot faster if you do it this way. It puts a little bit of more time up front in making your solutions so you can then go in and just get all of your observations or all of your analysis right away. Okay? So, what you will need to get from the stockroom is volumetric pipettes. You'll need a 25 mil, a 20 mil, 10 and 5 mil pipettes. Okay? You will also need volumetric flasks, a 50 mil and then 3 25 mil flasks. Okay? Which means your hands are going to be extremely full of glassware, because you'll also have your unknown sample. So it may not be a bad idea to do it in kind of waves, so that you can pick up, say, the 3 volumetric flasks and then get the 3 pipettes. Okay? I don't know how he's going to pass them out. Okay? With those, you can then go through and make your solutions. Part A, you're going to make your standard stock dilution solution. That was kind of fun, which you guys didn't think was fun. I thought it was fun. Okay? That solution is going to be our initial test. Okay? So part B has you go back and take that solution and evaluate it. Okay? What we're going to do is try and find the correct spectrum of light to use to determine our absorbance. Okay? Why is that necessary? Well, does our compound absorb all light equally? No. So if we go in and say, I want to look at how the absorption changes at 800 nanometers. Okay, 800 nanometers is relatively red. Would we expect our compound to absorb any light there? Probably not. Which means, what's the absorbance at that value? 0. What happens if we change the concentration? It's still 0. So part B is trying to find the maximum absorbance value, so that when we go through and do all of our dilutions, we actually see an absorbance. Okay? So the whole goal of part B, is to take your 50 ml volumetric flask, the initial solution that you make from part A, and to test that across the full spectrum. Okay? Very, very tedious, very, very slow. When you start to do that process in the room, I'll help make sure you get set up with that. Okay? It's going to be put sample in, record. Take sample out, put blank in, 0. Take blank out, put sample in, record. Take sample out, put blank in, 0. Take blank out, put sample in, record. Take sample out, put blank in. Okay? Very, very tedious. You're looking at 50 measurements of that. Okay? Not particularly fun, but that will help you to get the correct wavelength at which to monitor your other solutions. Once you know what that value is, you can immediately take the solutions that you've already made and do the absorptions values, do the rest of part C. Okay? That's my recommendation. You do not have to do that. You can do it in the exact sequence that the lab tells you. I just think you're going to end up wasting your time that way. Yes?
For storing these solutions, if they don't get finished, how do you know?
We have a bunch of small polyethylene bottles that if they aren't in there already, the stockroom will supply for us. And you'll be able to store them in those. Other questions? Okay, one big thing about storing stuff. You will have probably 4 to 5 bottles, all with blue solution in them. What's the concentration in each solution? Good question. How are you going to know which solution was which? Put labels on your solution bottles so that you know what you're looking at. Otherwise, you'll have to go through and remake all of the solutions and then redo that blanking thing. No, you wouldn't have to do that. Okay? Questions about that? Okay. So, part B is just trying to find the best place to monitor your reaction. Okay, so you'll use your 50 ml stock flask. Part 2C, step 4 is where you start creating your Beers graph. So that's absorption and concentration. Okay? Procedure can be a bit confusing with making those solutions, so if you've got questions, stop and ask. Okay? Make sure that you know exactly how you mix those. Part 2D You're going to then go through and make a new unknown sample. That's going to be with more nitric and sulfuric acid to go through and make an unknown sample that you can then test spectrophotometrically. Okay? Questions about any of that? Okay, here's your quiz. Earn your 50 points. What are you guys going to start with? Unknown solution for which experiment? I don't like first one. Give me more than that. The Electro one. Okay. Get that one set up, ready to go. Hopefully it'll all dissolve. The first 6 to get done with that, might even be 5. We'll throw you onto the electrolysis machines. The rest of you can immediately start making your solutions for the spectrophotometric one. Okay? This will be all individual. If you do want to share glassware, I'm fine with you sharing glassware, but everybody needs their own unknown. Okay? Yeah?
How many days are we doing